satisfy a time-dependent vector field. So again, we need to review some notations, right? Last time, what did we do?
We did like the maximum distance interval, right?
Yeah.
And then we ended up being that it's the LR, the open interval LR, where we defined L as.
Yeah, so we found the by construction method, right? We found the maximal interval of existence for a system. Right? So found the interval where the solution has exists, where solution exists and unique.
Unique,
Yeah.
yes.
So
well, we assumed uniqueness from 3.1.
Yeah, from 3.1 or they have uniqueness and existence of a solution. But the last time we gave a theorem that shows there is a maximal interval of existence of a solution. Yeah, so just from the largest possible interval on which there is a unique solution, right? Yeah, so that's what we did last time. So today first let's review the notation. Here is the notation. B is the domain of the vector field, right? Vector field. So here is alpha. So this is alpha represents the solution on the maximal interval. So any questions with the solution? So this I see is the maximal interval of existence. It's a time interval. Time interval. So this is a solution, right? Depending on time. Alpha curve. So from this time interval, so that's the maximal interval of existence. So from here to some set, which is a subset of Rn. Okay. So certain let this one be a solution. Passing this initial point. Yeah, so this is the initial point. That means at this time, right, at S, this curve will satisfy this when time equals S, the alpha will equal to C.
Alpha of T or alpha of S?
Yeah, alpha of S is C. C is Rn, right? C is an element in Rn. Yeah. So that means this, because the system is this. This is the vector field. This is the time-dependent vector field. So when time is some point, so we can put a S. Yeah, so that's the system. Initial value problem. So when time is S, X is C, right? So this also this system, that's the solution satisfying equation and the initial condition. So if alpha is the solution, then alpha can satisfy this. You can, in place of X, you use alpha. Let's just write alpha, which is a notation, just the notation for solution. So here we put alpha. It's X. Yeah, so far no problem with the notation, right? Solution Yeah, certainly the vector field is time dependent. So you see this vector field is defined on B, right? B is actually this set. This is a subset of some real number, right? T is some real number. This is Rn. Yeah, so B is where the vector field is defined. SC is just for the time. When time is S, the alpha is C. So this is actually R cross Rn, right? This is the point. So the integral curve will pass that point. Okay, so here we have a definition. But so far we are thinking of the maximal integral curve, right? Not just any integral curve satisfying this. So we just find the maximum possible interval where we have a solution. So this is the maximum interval, right, passing, including this point. And on this interval, there is a solution associated with this interval, right? That's a solution. So that's called a maximum integral curve. Okay, so here, definition, we define a set. So here D is a subset. This notation D is a subset of R cross Rn. Okay, here's how it is defined. T is a real number, means a time parameter, right? S is another real number, also corresponds to time at when time is S. So X is the vector represents position, for example, right?
Right. And
Yeah.
then it's
As X.
it has n components, right?
Yes, n component. This is a one Rn.
So why would we need two different times?
Yeah, we will clarify that
Okay.
in a few minutes. Yeah. So here, this is a real number, right?
Mhm.
This is a real number, and then Rn. But we just look at those. Yeah, so let's see. B and this set. So this, here we define a subset of this set. So this set, the first element, real number, and Rn, right? Some number in Rn. So we pick all those that if your Sx, this one, is in the domain of the vector field. See, remember what is the domain of the vector field? B. Yeah. Just any point, right? You see, you just look at the vector field is X, capital X. So in order for capital X to be defined, so this T, Rn, so you pick a point. We call it Sx, right? Sx are from the domain of the vector field. Otherwise, the vector field is not defined, right? So just to make sure that we pick in that notation S, X are from domain of the vector field. Then for any point in the domain of the vector field, you can find an integral curve. Yeah. So just for example, if you fix one point, right, then you can denote the integral curve passing this point by alpha Sx. That's our notation, alpha Sx. Currently, we're using Sx for the point, right? It's the only difference. So we have an integral curve, alpha Sx. And where is the curve defined? On this interval, right? That's the maximal interval where the integral curve is defined. It's a time interval.
So at any time t in that interval, we can find alpha of t such that it's a solution.
Yes, for any t from this interval,
It is a solution.
It's a solution.
Right.
Because the solution is just alpha as a function of, depending on t, right? Yeah. So, yes, so you see this is a subset of that such that this part has to be from the domain of the vector field. And from this point, you can have an interval or a maximum interval. So t has to be in the maximum interval of the solution, passing this point. Okay, so that's a set. We just defined a set. Actually, the flow is defined on this. This is the domain of the flow. So let's now question before we go further. If the vector field is a complete vector field, what is this set? If X is a complete vector field, last time we give a definition, right?
Then it's all the reals, right?
Yeah, will be all real numbers. So, because if X is a complete vector field, that means for any point from the from where? From the vector field, right? Domain of vector field. You pick any point, then the solution will have a maximum interval of existence being real number, the entire real number line. Yeah, this will be R, the entire real number line, on which solution is defined. Yeah, so that means this will be R. So T from R, so then this immediately will be R. The whole set will be R cross B, right? This is a point from the B, domain of vector field.
So t is any real number?
Yeah, so this, in that case, D is simply R cross B. This. Yeah, in this case. Okay, now let's just be familiar with the notation, right? So we look at a very special case. In that case, domain is this. So now let's define the flow. The flow generated by the vector field. By the vector field X is this map from this domain to Rn. Okay, which is defined by T as X equals alpha as X T. Okay, so that's the domain of the flow. This flow, you can see how many variables in here. T, right? This time. That's another time, actually, right? S. Yeah, so we interpret this one as a point, right? A time. That's another time. X is the position, right? X. Yeah, so here's the flow. So define on this. You have a set. On the set, we define V to be just the solution curve. Right? Flow is a solution curve. If you fix this point, is that a particular solution curve? This one, yeah. Look at this. And right now C is replaced by X, right?
Right.
Yeah, we allow X to be different. That is